Okay, let's get started here. Before we sort of dive into the new stuff, let me talk about what we did last time, these carboxylic acid derivative conversions. And in particular, I just want to clarify something. When I was writing your homework, we talked about how some of these you can get away with using the weak nucleophile version of whatever nucleophile you need, right? And other times you need it to be the strong nucleophile version. So the more I dug into it, there was a lot of like devil in the details that were a little murky. So what I decided to do for your homework is I'm just always going to ask you for the neutral version of whatever nucleophile that you need. All right, so just to kind of make it simple, so everybody take a second and tell me the neutral version of whatever nucleophile they need in order to make this carboxylic acid derivative conversion happen. Right, so these are these substitution reactions. We need to substitute this, which will be our leaving group, for this. So what's our nucleophile that we're going to use? It just simply needs to match what it is we're trying to attach here, right? And again, if I'm going to do the neutral version of that, I will use methanol. Okay, because notice how what I boxed in orange on my product side matches what I boxed in orange for my nucleophile. I just made it neutral, right, by adding that hydrogen. Cool. Okay, where we left off last time was talking about Fischer esterification reactions. This is how we can freely convert between carboxylic acids and esters under acidic conditions, right? Remember, we did this reaction in one specific direction. We could also do it in the other direction depending on what we added, right? So if instead we started out with our ester and we added in a bunch of water, that would push the reaction in this direction. Or we could start out with a carboxylic acid and add in a bunch of alcohol, and that would push it towards our ester product, right? So we called this dynamic equilibrium that we can tune to go in one direction or the other depending on our reaction conditions. All right. There's another one that we can use called saponification. Has anybody ever heard of this before? Yeah, okay, so this is how you make soap. All right, back in the day, they took animal fat and they treated it with lye, which is sodium hydroxide, and that's how they created soap, okay? So this is a way that we can convert an ester to a carboxylic acid. But this one is irreversible. All right, and the reason that it's irreversible is because it occurs in basic conditions. All right, so why are these basic? Under acidic conditions, we can freely convert back and forth, but under basic conditions, it goes only in one direction, right? So why is that? Okay, so let's take our ester and let's look at our mechanism and let's see if we can't figure this out. So, what do we think our nucleophile is going to be in this reaction? The hydroxide, all that negative charge. And what's our electrophile going to be in this reaction? That carbonyl carbon. All right, so do that first step for me. All right, we get our tetrahedral intermediate, and what are we going to ask ourselves? Do we have a good leaving group? Now, to be clear, both of these oxygens, from an energetic standpoint, are identical leaving groups, right? In both cases, we're going to choose, kick off a negatively charged oxygen. However, if I did this step here, where would that take me? Right back to the beginning. Okay, so that will absolutely occur in a good, 50% of these tetrahedral intermediates will then take one step back, right? But the other 50% will take one step forward in our reaction progress and kick off that alkoxide ion. Okay? And we got our carboxylic acid. So what's the problem here? I mean, this seems great. This seems exactly like what we did before with our acidic condition mechanisms. But the reaction doesn't just stop here, because what's going to happen to this carboxylic acid, in basic conditions? It's going to be deprotonated, right? So we're going to have an acid-base reaction, because this is a carboxylic acid. And we're going to have that hydroxide go ahead and pull off this proton. Right? And so in this saponification reaction, our product, if we're being really good, is not a carboxylic acid, but a carboxylate ion. And granted, we could turn this into a carboxylic acid by changing our conditions very easily, right? But the point being is if we look now at this carbonyl carbon, remember, what is the property that makes electrophiles good electrophiles? Is that they lack electron density. Well, as soon as I put a negative charge there, that's going to get passed back and forth between those two oxygens through resonance. All of a sudden, this carbonyl carbon is no longer a good electrophile. So you could add all the alcohol in the world that you wanted to this reaction mixture here, and it would not push that reaction in the reverse direction because you've just lost that electrophilic center, right? Your carbonyl carbon is no longer going to be accepting pairs of electrons. All right, so again, under acidic conditions, we can go back and forth, no problem. Under basic conditions, it's only going to go in one direction, from ester to carboxylic acid, or if we're being really good, what we would call a carboxylate ion. So, keeping this in mind here, let's now think about our carboxylic acid to amide conversions. All right, so given what we discussed about our carboxylic acid derivative conversions, Everybody take a second and tell me what I should use in this reaction here. All right, what should I use? Ammonia, NH3. All right, but I will tell you, this is absolutely not what's going to occur. Okay, so let's think about why this is. Let's take our carboxylic acid and let's mix it with ammonia. In order for our carboxylic acid conversions of carboxylic acid derivatives to occur, our ammonia has to play the role of a nucleophile and attack that electrophilic carbonyl carbon. And ammonia is a good nucleophile, right? But what else do we know about ammonia? It's a base, exactly. And what's going to happen when we take that basic ammonia and mix it with that carboxylic acid? We're not going to have this nucleophilic attack, because within 0.0000 whatever, 1 femtosecond, there's going to be this immediate acid-base reaction, which again is going to convert that carboxylic acid into a crap electrophile, that carboxylate ion, right? So there's not going to be any nucleophilic substitution. Instead, we're just going to have an acid-base reaction. Okay? And not only, I mean, there's two problems here now. Not only is this thing a bad electrophile, but ammonium doesn't even have a pair of electrons anymore. Right? It cannot play the role of a nucleophile. But let's say your boss is on you. They're like, look, you got to figure out how to convert this carboxylic acid into this amide, right here. How would you do it? You could do an ester, you could, and that would perfectly work, especially on pencil and paper. It would take a long time. It would be one of the lesser efficient ways, because you could turn it into something way more reactive really easily, right? Remember that carboxylic acids are the one way that we can go back to that acyl chloride by using that thionyl chloride. Honestly, the ester idea is also correct. You could do it, right? But this would be the way more efficient way to do it, is to first turn it, right? We can freely convert it into that most reactive carboxylic acid derivative, that acyl chloride, and then treat that. We got to be good. We got to use our 2 equivalents. All right, but yes, if we really needed to do it, that's how we would do it. We just couldn't do it in one step because, again, you mix an amine and a carboxylic acid, you're going to get an acid-base reaction. Cool. All right. So now we're going to lump these last two into this category of other carboxylic acid derivative reactions. All right, so we talked about how we could go back and forth between the different derivatives. All right, now we're going to introduce some of our familiar reagents here. So what happens when we treat our carboxylic acid derivatives with a Grignard? Grignards we know to be nucleophiles. We talked about them with aldehydes and ketones. They attack that electrophilic carbonyl carbon. Well, hey, all of our carboxylic acid derivatives also have carbonyl carbons, right? So let's just see if we can't take an example here. Let's use that acyl chloride. Let's throw a Grignard in there. And let's see if we can't figure out what's going to happen by looking at our reaction mechanism. Okay. All right, our nucleophilic carbon is going to attack that electrophilic carbonyl carbon. And this is going to take us to that world famous intermediate, tetrahedral intermediate. Okay, I'm going to keep that Grignard carbon in red here just so we can make sure to keep track of who's who. All right, and what do we say when we get our tetrahedral intermediate? Is there a good leaving group here? There's the best freaking leaving group in the world, right? That chloride ion. So absolutely, this pair of electrons comes down, kicks off that chloride ion. All right, so I have successfully added those two carbons from my Grignard, and I've created what new functional group? A ketone. Cool. So the story doesn't end here, though. Why? What do we know about Grignards and ketones? They're going to react again. Absolutely, right? So this product that we've just created, this ketone, this is where we started talking about Grignards, right? So this is absolutely just going to react with yet another molecule of our Grignard, right? It's still got that electrophilic carbonyl carbon. So we'll just have a second reaction. And so we'll actually end up adding two equivalents of that Grignard reagent. All right, let me try to write a little smaller. And again, we get to that tetrahedral intermediate. And so we're going to ask ourselves what we always do, is there a good leaving group? But what's the answer this time? No, we only have carbons and hydrogens. You're going to be hard-pressed, well, they're actually only carbons in this case. You're going to be hard-pressed to kick off a carbon with a negative charge, right? So we're kind of stuck here. Right? And in fact, we're stuck until we do that second step, our acidic workup step, where we had some source of proton in there, right? And that proton will be accepted by that alkoxide. Okay, so again, what we get here is 2 additions of our Grignard, creating an alcohol. All right, so this is the case for a few of our carboxylic acid derivatives. Our acyl halides, our acid anhydrides, and our esters will all react with 2 equivalents of that MgBr, of that Grignard. Unless you started out, like the only exception would be if I started out with the teeniest, tiniest one where there was a hydrogen over here instead, and then it would be a secondary alcohol. But yeah, if there's any more than 1 carbon in your carboxylic acid derivative, it would be a tertiary alcohol. Cool. Okay, now the story is a little bit different when we start talking about our nitrogen-containing carboxylic acid derivatives. Okay, so let's take an amide here, and we're actually going to lump both amides and nitriles into the same bucket. We're not going to really look at a full mechanism here. Okay. But when we form our tetrahedral intermediate, and there's a little bit of proton transfer reshuffling that's going to happen, but the bottom line is we're kind of thinking about, oh, what's our good leaving group? Well, nitrogen's not a good leaving group, and it's a way worse leaving group than oxygen is. So what actually happens is we end up kicking off the oxygen instead of the nitrogen in this process. So what we get is this intermediate. All right, with that carbon-nitrogen double bond, we've seen this before. All right, we call this an iminium ion with an I, iminium, where we've actually lost that oxygen. We kicked it off, right? Because comparing oxygen and nitrogen, oxygen is the better leaving group. Okay. And we've talked about how these imines form when we react aldehydes and ketones with amines. Okay, but that reaction is reversible. So when we do this hydronium step here, we actually kick that nitrogen back off. And so what we're left with in this case is a ketone. All right, so what's a little bit weird here is that we get this iminium ion intermediate, again, because nitrogen is a worse leaving group oxygen. But then when we do that acidic workup, we add a whole bunch of water and aqueous hydronium ions. That aminium ion gets converted back to our carbonyl. So with amides and nitriles, we have one addition and that aldehyde or ketone product. Did you guys do a Grignard reagent in the lab? Cool. All right. What is the first thing that you had to do with your glassware? Yeah, you had to be real paranoid about any source of hydrogen contaminant, right? Okay, cool. Because that's going to lead us into our last one here. What happens when we take a Grignard and mix it with a carboxylic acid, right? The problem is that Grignards are not only good nucleophiles, they are also good bases. And so they will steal any source of proton that is available, which is why they are just straight up incompatible with carboxylic acids, all right? If we did take a carboxylic acid and we reacted it with our Grignard, we would deprotonate that carboxylic acid to create that carboxylate ion. Oops. All right, and to be clear, our proton acceptor would be that carbon. So we just had a very expensive roundabout way of creating an alkane and a carboxylate ion, right? So this carbon, I guess we can draw it on there explicitly. Our hydrogen from our carboxylic acid is now going to be bound to that nucleophilic carbon. We really pretty much just wasted our Grignard by adding in with that proton source. So with a carboxylic acid, we do not get our intended nucleophilic attack. We instead get an acid-base reaction. That creates a carboxylate and an alkane. And if you really want an alkane, there are way easier ways to do it than turning it into a Grignard, right? Cool. So we talked about how Grignards react with our carboxylic acid derivatives. All right, now we're going to look at lithium aluminum hydride. And what we want to remember about lithium aluminum hydride is that it is a reducing agent. All right, so again, let's take one of our carboxylic acid derivatives. We'll start with that most reactive acyl chloride. We're going to add in that lithium aluminum hydride. It's really just the aluminum hydride portion is the important part. And remember, what makes these hydrides, when you hear hydride, you want to think, I got a nucleophilic hydrogen, right? That's what's so weird about these hydrides, is this is going to play the role of the nucleophile and attack that electrophilic carbonyl carbon. Okay, so now based in analogy of what we did with our Grignards, I want to see if he can't finish off this mechanism. I'm going to give you a few minutes. I'll kind of quietly start filling it up here, all right? But based on what we did previously, see if you can't figure out what we're going to have in our reaction. All right, so we kick off that good leaving group, that chloride ion, and that leaves us with an aldehyde here. But then what do we know about aldehydes in the presence of lithium aluminum hydride? They will also be reduced. So just like we saw with our Grignards, we're going to have another round of nucleophilic attack, creating another one of our tetrahedral intermediates. And we get here and we ask ourselves, do we have a good leaving group? Well, neither carbon nor hydrogen is about to play the role of a leaving group, so we're stuck. All right, and we're stuck until we do that second step, where we add in that acidic workup, that aqueous acid. All right, and so again, we have this alcohol product, but a much less substituted alcohol. We just have a primary alcohol. And I'll put these hydrogens on here explicitly, but of course you don't have to draw those in. You could have just given me the formula for ethanol, or the structure rather. Okay. So, let's just make note here. And again, we can put a few of our carboxylic acid derivatives into the same bucket. Our acyl halides, our acid anhydrides, our esters, and actually our carboxylic acids too. Lithium aluminum hydride is not about to accept any protons. It's only a nucleophile, not a base at all. All right, all of these will undergo these two equivalents of the aluminum hydride to form alcohols. Okay? So again, we have sort of something in like direct analogy to what we saw with our Grignards. We first have this attack and form our tetrahedral intermediate. That kicks off that good leaving group, that chloride ion. But then what we're left with is just another susceptible carbonyl carbon, right? An aldehyde. And so that's going to undergo a second round of attack, producing our alcohol product. All right, and then the last bucket is our nitrogen-containing carboxylic acid derivatives, our amides and our nitriles. Okay. We had actually talked about nitriles and our reducing agents before. We don't have a mechanism here. I know you're super bummed. All right, but this again undergoes a reduction reaction here, but we don't have any oxygens or anything like that, right? So instead we're just going to fully reduce this carbon in the same way. But what's our product going to be instead of being a alcohol? 1, 2, 3, 4, 1, 2, 3, 4. Yeah, we'll have an amine. And it turns out that if you took a 4-carbon amide and you treated it with that same reducing agent, it would also fully reduce to an amine. All right, so we're actually going to lose that oxygen, that better of the two leaving groups in this process. So amides and nitriles, these get reduced to specifically primary amines. Okay? 1, 2, 3, 4. 1, 2, 3, 4. Yeah. Cool. All right. So, just to summarize here. One, again, with regard to your homework and these conversions of carboxylic acid derivatives, I specify in the problem, I just want you to tell me the neutral form of the nucleophile that's required to do that carboxylic acid derivative conversion. Kind of the more I dug into it, the more there was, shaky rhyme or reason as to what you had when. So we're just always going to default to the neutral version. All right. We talked about these talked about Fischer esterifications first, converting an ester to a carboxylic acid and back again under acidic conditions. And then we have these saponification reactions where we can convert a ester to a carboxylic acid, but this time irreversibly. right? And why it's irreversible is because of this very last step here, where we're going to deprotonate that carboxylic acid that's formed to make our carboxylate ion. And your carboxylate ion is no longer going to play the role of an electrophile. Too much electron density to be an electrophile. Okay? We also then talked about carboxylic acids are kind of the pain in the butt ones here, specifically because they are acids, right? So if we took a carboxylic acid and tried to mix it with an amine, we would think we would get this amide product, but no, instead we're just going to get a simple acid-base reaction. And again, your acid-base reaction creates this terrible electrophile as well as a terrible nucleophile. All right? And then we're going to sort of lump all these other ones into these other reaction categories, going back to our familiar reagents, the Grignard and the lithium aluminum hydride. We talked about how Grignards react with acyl halides, acid anhydrides, and esters, undergoing 2 rounds of nucleophilic attack, giving us this twice substituted alcohol product here. If we have amides and nitriles, because of that nitrogen on there, which is a terrible leaving group, we get this kind of weird iminium ion intermediate. And once we do our acidic workup, we're going to be left with a carbonyl group instead, right? So we'll only actually get one addition of that Grignard, and we'll get this either aldehyde or ketone product out of it. And then lastly, we said carboxylic acids, again, pain in the butt, because Grignards are actually good bases as well. So we really just ruin your Grignard here if you add it in with a carboxylic acid. You would get a carboxylate ion, which needs a negative charge, and our alkane. All right, and then lastly, our reducing agent, lithium aluminum hydride. We can reduce acyl halides, acid anhydrides, and esters, and carboxylic acids to primary alcohols because it undergoes 2 rounds of addition with that, or nucleophilic attack with that aluminum hydride, with that nucleophilic hydrogen. And if we had our nitrogen-containing ones, amides or nitriles, these also get reduced, but they get reduced to primary amines. And with that, congratulations, you're done with your Organic Chemistry 2 course. Cool. All right. Like I said, we'll do a review session on Monday of next week, and on Wednesday of next week will be this optional exam viewing session.